Hey everybody, so today I'm going to be going over some of the crypto challenges for the Hack The Boo CTF. So my aim with this video is to try and kind of do it from like a general perspective. So I'm not going to get like super in deep or like super mathematical or anything like that. Just give you an idea of kind of what's involved in the challenges if you weren't able to solve any of them, or just trying to understand more about what's kind of going on behind them. So yeah, hopefully, I know that's the aim of this video, so hopefully you get something out of it. Again, I'm on a like janky laptop setup here, so if the sound sucks or the resolution's terrible, or I apologize. So anyway, let's go ahead and take a look at the challenges. I think day one was this Gunna Lift Em All challenge. And if we look at the challenge, basically, make this bigger. What we're given is these public key variables, and then the C1 and C2. And if we look at what's going on here in the parameters to generate the public key, we see this is what would be like a discrete logarithm kind of setup. So we're given a random 1024-bit prime, and then we have the G, which is G is just kind of the standard convention for the base. It's just from random element, X some random number, and we're taking H, which is G to the X mod P. So you'll see there's a lot of like cryptographic primitives built around discrete logarithms, and the reason is it's kind of like it's a one-way function. So it's very easy for us to compute what H is if we know these G, X, and P. But if we're given H, G, and P, it's computationally infeasible, assuming we've set everything up right, for us to go backwards. So if we know what the modulus is in the base and we know what the answer comes out to be, we can't work out what X is. So X is kind of like the private key, or the secret information that allows, with that knowledge, it allows one to perform the task that is computationally infeasible without it. So we can freely give anybody these variables and they won't be able to figure out X. So then we see in this encryption function, what they're doing is just then taking that H, raising it to the power of Y, that same modulus, and they're converting M to an integer, and then they're going to give us G times Y mod P and in M times S mod P. So if we look at it here, sorry, the other thing I don't have on the setup is a mouse, so also kind of annoying. Anyway, so we have that G is congruent to, oops, did that backwards. H is congruent to G to the X mod P. And then we had S was H to the Y mod P. And then we had C1 was G times Y mod P. And C2 was M times S mod P. And so I'll write down what we know. Our knowns are, we know G, H, P, C1, and C2. Well, so clearly what we need to do, what we're trying to do here is we need to figure out M, right? Well, it's pretty straightforward here. We have a modular equation. So what we can do then is, if we multiply both sides by the inverse of S, we could solve this. So we could do C2 times S inverse is congruent to M times S inverse. So if you're unfamiliar with modular arithmetic, since you can't divide, since we're working over the integers mod P, you have to use multiplicative inverse. So all that bit essentially means is it's the number we multiply another number by in order to make them to equal 1. So like S times S inverse is just going to equal 1. So essentially we're just kind of like canceling it out. So what we have then is mod p. So if we can figure out what s is, we can calculate its inverse, and then we can just multiply it by C2, and that'll give us the answer, right? Because m is what we wanted. So now it becomes a problem of trying to figure out what s is. So we know that s is h to the y. So when we know what h is, if we somehow knew what y was, then we could solve this and know x. Well, if we just look at this other equation they gave us, which was g times y is congruent to c1, well, we know what g is, so we could just we could do the same thing. So we could take c, the inverse of g, multiply both sides by it, and so like those, that's going to become equal to 1. So then we have y is congruent to the inverse of g, c1 mod p. So now we can solve for y. Just multiply c1 by the inverse of g, and then we can take y and plug it into here because we know h. So then we can get s. We can calculate the inverse of s, and so that gives us this value right here. So then we simply solve this equation to get the answer. So I'm not actually going to do all that, but that's kind of how it works. So, and it's easy for us to calculate inverses. An inverse exists as long as the number, so there's an inverse for s if s and p, if the greatest common divisor between them is 1. But since we know p is prime, all the numbers less than p have a GCD of 1 with it. So an inverse will exist, and we can calculate it easily. We just use Python to do that. Just raise it to the power of -1. But if you want to learn a little more about it, the way you do it is using the extended Euclidean algorithm. Yeah, so basically that's kind of all there was with that one. So if we now look at what was day 2, I think day 2 was Carmichael. So if we look at this, what we see here, we go down to the main function, right? So it's asking for some value p, and we're going to give it p. It's going to convert it to an integer, and then basically if it passes this check, we get the flag. So it has to not be prime for this prime function, and this prime function is the one that comes from PyCryptodome. So essentially we need a number that's not prime, but we need it to pass their custom is prime function. So if we look at the custom is prime, so essentially, okay, here we go. It needs to be a number between, it needs to be greater than, oh yeah, so it needs to be greater than 600 bits and less than 1500 bits, so fairly large number. And then it can't, or we want it to pass this Miller-Rabin, right? Because we want Miller-Rabin to come out as true, which will turn this to false, so it won't go there and it'll return true. So essentially what we need is a number that is not prime, but this Miller-Rabin function thinks is prime. So Miller-Rabin, if you're unfamiliar with, is a pretty famous probabilistic primality test. So I won't really go over how it works, but I'll show you kind of an example that will give you the idea. And so go back to there is something called Fermat's Little theorem. And essentially it states that if we have some base A and we raise it to the power of p minus 1, that is going to be congruent to 1 mod p if p is a prime number. And so if A and P don't share a multiple other than 1, then and P is prime, this will equal 1. So you could kind of see how we could use that for a primality test, right? Like we could just take if we were trying to figure out if P was prime or not, well, we could just pick some base, raise it to the power of P minus 1, and if we get 1, then sweet, it's a prime. Except that's not quite how it works. So it's not, I forget the name of it, but that's not true. But what is true is the converse. Like if this is not 1, like if we raise some number to the power of P minus 1 and we don't get 1, then it is most definitely, it is not a prime number. So really what we have here is a test for compositeness. So if a number isn't prime, then we can test for certain whether a number isn't prime. Well, we'll know if a number isn't prime if this ever comes back 1. But there's kind of a problem in that it's not guaranteed that a composite number will give you something other than 1. So there are bases where we can take a composite P and do this on, and we'll still get a 1. So then we could try other bases. But then unfortunately, are things called Carmichael numbers, which is where the name of the challenge comes from, in that there are numbers that for every base, even though the number's composite, this will still come out to be true. So you can't use this to ascertain primality, because what you'll end up with is, the number's either prime or it's a Carmichael number. Now, Carmichael numbers are pretty rare, but there are infinitely many of them. So this test kind of doesn't do us a lot of good. Well, kind of. But so the Miller-Rabin test is kind of similar to this in that it is testing something like this, where if it comes out to not 1, then it knows, okay, P is definitely composite. And if it comes out to 1, then it's going to try a different base. The difference between Fermat's primality test and the Miller-Rabin primality test is that, so there are numbers, Carmichael numbers, where it'll always get 1. But for the Miller-Rabin test, there aren't any numbers such that for every base you always get 1. So that's also why the Miller-Rabin test is probabilistic, because you can never, unless you check every single base, you can't know for 100% certain whether it's prime or not, but you can determine with a high degree of probability whether it's not, because you just keep testing different bases. And so like actually if we go to Wikipedia, if we look up numbers, TV show I want to spell correctly. So if we see, we'll see here, here's what I just kind of wanted to show you. Should give some examples. Oh, that's actually not what I want. Sorry. You can tell a lot of planning went into this video. What I wanted to show you is so we can see here, right? So these are some examples where they worked everything out, right? So for any number under this giant number, it's enough that if we just tested these bases, we don't have to test all the bases, but if we test these bases, then it's guaranteed that every number less than this, these are all the bases we have to test. So the way Miller-Rabin works is it tests a bunch of different bases. And if if a composite number is passing the Miller-Rabin test, it's called a strong pseudo-prime, right? Because it looks like it's prime. So if we come back to this Miller-Rabin test, we see what basis is it going to use to test? And so it's using this generate basis function with 300. And I'm not going to go over this super a lot, but If you want to learn like what is going on here, this is actually, it's a prime sieve. So you could look up the sieve of Eratosthenes. Basically, the way it works, not exactly like this, but it's easier to explain this way, is it's just going to print, or it's going to create an array of truths that are in long. So in our case, it'll be 300 long, and it's going to check every odd number up to the square root of n, which would be like 17 and some change. So from 3 to 17, all the odd numbers. And then what it's going to do is start out at 3 and go, okay, 3 is true, and then it's going to, this isn't exactly what it does, but it's going to then turn every multiple of 3 after 3 into false. So it'll, 6 will be false, 9 will be false, 12 will be false, 15 will be false, etc. Then it goes to 5, and it's, if 5's true, then it's going to set every multiple of 5 to false, and it's going to do that for all the numbers. If it's true, then it essentially, what happens is you iterate across the array. If you get to a number in the array that is true, like if you get to an index that is true, that index is a prime number, and then you set all multiples of it to false. So that's what a prime sieve is. So what this generate basis is doing is it's getting every prime number below 300. So, and that's the basis for the Miller-Rabin function. So essentially what we need is a strong pseudoprime that is between 600 and 1500 bits long that will pass the Miller-Rabin test for the first, all the primes under 300. Now, there you can code up something that'll do that. It's not trivial. Like, you kind of have to read some math papers to like understand what's going on. So it's actually, there's a similar challenge on Crypto Hack, and it's worth like 200 points, I think. So it's not easy. I think the reason that this challenge is easy is, and so many people solved it, is we don't essentially have to do that work. We just need to find one of those numbers. So if you do a little bit of work on Google, one of the things we'll see is that in the Wikipedia page for Carmichael numbers, where is it? Somewhere on here. Oh, here we go. So this mathematician, in one of his papers, gives a 397 digit Carmichael number. So that is, I forget how many bits that is, but that'll be less than 1500 and greater than 600. That is a strong pseudoprime to all the prime bases less than 307. So that's exactly what we're looking for. So essentially all we need to do is take this number here, plug it into this formula, and the number we get out, all we have to do then is just send that number to the server. And there are a bunch of other numbers that'll work. So I don't know if you did some looking on Google, I'm sure you could come across some other ones. So I think that's why it was easy and solved so much. So there, that's kind of how this one goes. Hopefully that made sense. So the next one was the spooky RSA. I'm trying to remember what this was. Oh, so okay, so we're given an N and an E1C1 and an E2C2. And what we have is that N is a product of two 1024-bit primes. So N is 2048 bits long. And then E1 and E2 are random elements. And what is F? Oh, okay, private zero. So it is P. So F is just P here. So essentially, go ahead. Okay. So if we have that N is equal to P times Q, and then E1 and E2 are just random numbers, and we had C1 is congruent to p to the e1, and then they were adding m to it, which is the flag, mod p, and this isn't technically quite right, but p. And we want to figure out what m is. Well, if we look at these two equations, and I'll go over something in a minute, but just essentially it'll still work this way. But if we take these two things, these two equations, and we just subtract them from each other, we get c1 minus c2 is congruent to p to the e1 minus p to the e2 plus m minus m mod p. So, sorry, mod n. So we're left with c1 minus c2 is congruent to p to the e1 minus p to the e2 mod n, right? Because m minus m is just 0. Well, if we look here, we know they gave us c1 and c2. So when we subtract them, we end up with a real number over here. And we know that number is what p to the e1 minus p to the e2 is. Well, one of the theorems in number theory is essentially that if you have these here, these are both like p to the e1 is some, p, this has p as a factor, this has p as a factor, and we know n has p as a factor. So we know that c1 minus c2 and n, the GCD is going to be, well, technically just be some multiple of p, but most likely it's just going to be p. So we could take the GCD of c1 minus c2 and n and then get p. Well, they also gave us, so once we know p, they gave us e1 and e2, so we could plug that back into either equation, right? We just take p to the e1 and then subtract it from c1, right? So we have c1 minus p to the e1 congruent to m mod n. So we can just solve it like that. Now the reason I said it's not quite like that, but it still works out, is that technically, and maybe this is like gonna be too confusing, or I should just not do it, but technically what we had here was actually p to the e1 plus m mod n. We had p to the e1 mod n plus m mod n, and the same thing here. Like taking that, you might, the reason I just kind of wanted to go over this is because you might be thinking, well, like, are we allowed to do that? Because we did mod n first. And the reason this still works is by definition of modular arithmetic, what this actually is p to the e1 plus some multiple of n is congruent to c1. So, and then what we had then would be like plus m. And so we had the same thing here. Some multiple of n. We don't know what they are, but we can still subtract these two equations, and we have a p to the e1 minus p to the e2 plus k1n minus k2n plus m minus m. So now we're saying, like, these still all, there's two ways to look at it. These still all have a factor of p. So we can still do the same thing. But also, since we're working mod n, essentially these just go to 0 because there's some multiple of n. So yeah, I don't know. Maybe I shouldn't have gone over that because it might be I might have not explained it well, and maybe I'm just confusing you. But essentially, I just wanted to point that out in case you were looked at it earlier and we're like, well, that won't work because we're doing this other mod thing, or maybe we can't do that. So, but essentially we can is essentially what using the word essentially too much. So that just leaves us, well, there was 2 challenges, but I'm just going to go over so if we look at this challenge, what we see is essentially there's a bunch of different modes of encryption for AES. There's ECB, CBC, CFB, OFB, CTR. And we can pick a mode and get the encryption of the flag in that mode, and then we can also send plain text and have anything we want encrypted. So the first thing you might actually let me yes, block modes. I think this will have something I want to show. Yeah, so if we look at this is just regular old ECB. We might think like, oh, sweet, we can get the flag encrypted to us because the key never changes. And then we could just give that flag right back, and we'll say it's the plain text, and when they run it through the AES function, we'll get back out the flag. But the problem with that is what we end up with, where is it? When we go to encrypt a plain text, it encodes it. So this function right here turns it into a byte string. And since it's just regular parameters, it's going to use ASCII. Well, the problem is that when the flag is encrypted, essentially whatever comes out of the encryption function, you can just think of as a bunch of random bytes. Well, ASCII, any of the bytes over, it has to be a printable ASCII character in order for this function not to throw an error. So mathematically, it's just incredibly unlikely, I mean, virtually impossible, that we can just keep encrypting something. Like if we kept hitting the server up and it changed the key every time we established the connection, that we'll get one where the encryption of the flag, all the bytes are actual printable ASCII characters. So if you were thinking like, oh, sweet, I'll just use ECB, that's the reason ECB won't work. But if we look at, where is CTR? We want to use CTR mode. So CTR is what's called a stream cipher. Our actual plain text doesn't get run through the encryption function. What gets run through the encryption function is like a nonce and a counter. And then that gets XOR'd with the plain text. Whoops. So essentially what this means is if this is never, like if this gets reused, you get the same, what comes out of the block cipher, or what comes out of the AES function is called the key stream. So if this gets reused, you get this exact same key stream. So what we can do then is get the encryption of the flag, and then we want to know what the key stream is, because then we could just take the key stream and then XOR it with the ciphertext, and because of the rules of XOR, we would get back the original plain text. But we can't, so if we just sent it all 0 bytes for our plain text, anything XORed with 0 is just itself, so we would get back the key stream. But the problem is we can't send it all zeros, because again, it has to be encodable, and 0, the byte value 0 is not an ASCII character. But we can just pick any printable character we want. So if we just, whatever, pick all letter A's, I think that's 41 in hex, capital A. So we'll get 2 things. We will get the flag, and then since it reuses, every time we run the encryption function, it reuses the same counter. We can then encrypt all A's, And then what we get back will then XOR with all A's. So that cancels out the A's. Anything XORed with itself is 0. So that essentially cancels all that out. And then what we're left with is just the key stream. So now we know what originally came out of this encryption function. So then we can XOR that with the ciphertext of the flag, and what we get back is the flag. So I'm sure I did not probably explain that well, and that might have been confusing, but that's kind of the idea behind this one. So hopefully that sort of made sense, and if not, maybe at least gave you an idea of what to do or what to look up, or maybe it just satisfied your curiosity. So anyway, that's just, I'm not going to go over the fifth one because I just looked at it briefly and was like, I don't know, it just looked like you had to do reverse some bit shifting and stuff. And I don't know, didn't feel like trying to figure it out. So yeah, hopefully, I don't know, hopefully this video is not too crappy. I doubt anyone makes it to the end here. So, but if you're still listening to me, hopefully you got something out of this. And if you did and wanted to like or subscribe, that'd be greatly appreciative. Otherwise, yeah, like, thanks for listening, and yeah, take care.